Hello everybody. It's time to start talking about sequences, series, and power series. And we really need to talk about it because sequences are unlike anything that you have ever done in your life. And I'm wearing a shirt to help us understand that. So everyone knows the song 99 Bottles of Beer on the Wall. If you don't approve of beer, let's just make it 99 bottles of hand sanitizer, but the sound doesn't come out so well, but it's the same idea. So I'll just use beer because it's one syllable. 99 bottles of beer on the wall, blah, blah, blah. Take one down, pass it around, 98 bottles of beer on the wall. Duh. If you have an infinite number of bottles of beer on the wall, you take one down and pass it around, and you still have the same number of bottles of beer on the wall. When you take something away from an infinite number, the same amount remains. So everything that you might think about when it comes to working with infinite quantities is just, it doesn't work. If you take some away, you still have the same number. You can have things that are obviously much smaller than other infinite things. The big example is the rational numbers, the things formed by fractions a over b, where a and b are integers. And the integers, clearly, there are many, many more integers than there are rational numbers. Wrong. Same number. You can put them into a one-to-one correspondence, and so you still have an infinite number of rational bottles of hand sanitizer on the wall. But let's see what this has to do with sequences and series and the like. First of all, we're not interested in sequences and we're not interested in series. So let's cut to the chase here. What we're interested in are power series. Power series look like this. We have, I'll have to write it out, sorry. You have an unknown x, which you will see in a second. And what you do is you write an infinite sum that looks like this. You have a constant a sub 0 plus a constant times x plus a constant times x squared plus another constant times x cubed. So far so good, only we're going to keep doing this out into infinity. The reason we want to do that is so that we can use this to solve differential equations and other kinds of problems. And so we need to be able to push the difficulties out to infinity. So there's our basic power series. But in order to understand that, we have to understand numerical series. And in order to understand that, we have to understand sequences. So the order of things that we're doing: sequences, series, that's numerical series, then power series. Keep your eye on the prize, which is power series, which are, pardon the pun, a very, very powerful technique for solving a lot of practical problems. So we would like to get at power series. So I've lied a little bit. I said everything you know about infinity is wrong. That is not true. There is something you know about infinity that is correct, and that is this. This is the limit of Archimedes. And so the limit of Archimedes says that the limit as x goes to infinity of 1 over x is 0. This obviously is a very, very old result. It goes back to Archimedes, like 400 BC or something. And so, I might got that date wrong. Don't at me. So this is something that you do know about infinity. And so this is pretty much our big tool, and that's going to be the thing that gets us. Now, there's a lot about this in the book. I don't want to put this in this video, but that is what made this work. Okay. Now, why are we interested in power series? Power series are easy to take the derivative of, and they're easy to integrate. And so that gives them a big advantage over other things. If you have something kind of arbitrary, I mean, even sine, it took Cauchy a long time to figure out how to take the derivative of sine, and it involves this very, very important limit. So power series, and eventually we will have a power series for sine, are easy to take the derivative of. Let me show you what's going on there. I'm leaving aside all the stuff about whether this converges or not, because I want you to understand why this is useful. So let me write out a power series, and we can fuss about the notation later, but it's easiest just to show the first few terms and then imagine what's going on. When you imagine, you have to keep in mind that everything you know about infinity is wrong, so imagine carefully. Okay, here's our power series. We've got some function f, a sub 0 plus a sub 1x plus a sub 2 times x squared, so forth and so on. And at the end, we have the dot, dot, dot saying we're going to keep doing this forever. And that actually helps us solve a lot of problems because we just keep kicking the can down the road. So that's what's going to happen. Let me show you how to take the derivative. Let me show you how to take the integral. And then that might convince you that this will be something worth putting some effort into. And you'll have to, because everything you know about infinity is wrong. Okay, the derivative, f prime of x. We're just going to do that term by term. And a lot of the fancy math people are going to say, well, you have to justify that. No, we have to justify justifying it by showing that it's useful. So let's just take the derivative, and that's easy. Derivative of a constant is 0. Derivative of a1 times x is a1. Derivative of a constant times x squared is 2 times the constant times x, and so forth and so on. So let me write that out. And I'm going to write it in kind of a funny way to emphasize something. Okay. Well, we don't have forever, so I'm just going to write some dot, dot, dots. So there's the derivative. I just take the derivative of each term and keep adding. For a polynomial, for a finite series, one that eventually is all 0, that's all you need to do. You've been doing this for quite a long time, and so that's fine. The integral part is going to be strange. Well, it will be and it won't be. I want to take the integral of f of x dx. And so, and I'm still using the same thing with the coefficients being a's for f. And let's see what happens. Well, first of all, when you do an integral like this, there's always a constant term. So usually we throw that in at the end, but let's throw that in at the beginning. That'll make sense in a minute. Okay, so we're going to have the constant, the c, that's the unknown constant, and then we'll just start integrating. The integral of a sub 0 is a sub 0 times x. And the integral of a sub 1 times x is a sub 1 times x squared over 2. And the integral of a sub 3 times x, a sub 2 times x squared is a sub 2 times x cubed over 3. So let me write that out. So we got a1x, a0x, I was reading the wrong line, a1 x squared over 2, and then a2 x cubed over 3, and let's just do one more, a cubed x to the 4th over 4, and we'll keep going that way. And so there's the dot, dot, dot saying we're going to keep doing this forever. And we'll see what's happened here is you've got an x and an x squared and an x cubed and an x to the 4th. You can neaten these up in different ways. Where is the x to the 0 term? Where is the constant term? That's the constant of integration. And so this enables you to do any of the things that you might do with an integral as opposed to just an indefinite integral like this. So start with a power series. Derivatives a power series, integrals a power series, pretty straightforward as far as the term-by-term calculation, and we'll go by that. So let me just finish, because something that is one of my favorite things in all of mathematics is on this page, and it would be criminal to not emphasize it. So hey, at least we're not live. Okay, but I'm not going to re-tape it anyway. So what I've put in this red box is the tangent line approximation to f at the point 0. And you can see that right away because you would have the value of f and then the coefficient here. And if you look at the derivative, if you evaluate the derivative as 0, all of these terms become 0, and all that's left is a1. a1 is the derivative of f at 0, and so the beginning of this series is the tangent line approximation, which is about one of the most important things in the universe. So We're going to do all this stuff with series so that we can understand power series. We're going to do this. We're going to solve some differential equations and some other kinds of problems, and also find some other kind of neat and interesting stuff. So that's the deal. Talk to you soon.